Dank u wel. Zet hem al aan? Ja. Goedemiddag. Good afternoon, everybody. Please take a seat. Be relaxed. Except for Vincent, of course. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you all to the public defense of Vincent Vanlaer. Vincent Vanlaer has presented to the faculty his PhD thesis on the topic Structure and Internal Rotation of Pulsating Stars, in partial fulfillment of the requirements for obtaining the degree of PhD in Science, Astronomy and Astrophysics. In a moment, Vincent will publicly defend his PhD thesis, but before he can start doing so, it's my pleasure to introduce to you the members of the examination committee. For you, on the right, Professor Connie Aerts, who is the promoter of Vincent. Connie is affiliated to the Institute of Astronomy in the Department of Physics and Astronomy here at the University of Leuven. Then to my left here is Professor Tim van Holst. Tim is affiliated to the Royal Observatory of Belgium, and he is as well affiliated to the Institute of Astronomy here at the University of Leuven. Also member of this PhD examination committee is Professor Tom van Doorselaere. He is affiliated to the Division of Plasma Astrophysics in the Department of Mathematics at KU Leuven. Tom is excused for the meeting today. He unfortunately couldn't be here, but he did participate in the first meeting that we had with Vincent a number of weeks ago. It's also a pleasure to welcome two examination committee members from abroad. And first here on my left-hand side is Professor Richard Townsend. Richard is affiliated to the University of Wisconsin-Madison in the United States of America. And then next to him is Professor Jørgen Christensen Dalsgaard from Aarhus University in Denmark. And I welcome all of you in this examination committee. I have the pleasure and the honor to be the chair of this examination committee. My name is Christian Temst. I'm affiliated to the Quantum Solid State Physics Division, also in the Department of Physics and Astronomy at KU Leuven. So, we're about ready to start. Vincent, you will now publicly defend your PhD thesis. You're invited to give a presentation of about 45 minutes about your work. After the presentation, first of all, the examination committee will ask questions. And since this is a public meeting and a public defense, after the questions from the examination committee, everybody is also free to ask questions to Vincent. So I hope you will all enjoy the presentation and the defense of today, and I give the floor to Vincent.
Okay, thank you for the introduction, and thank you all for coming here, both everyone here in the room and everyone online. And I'd like to start with something that Christian mentioned. So the PhD that I hopefully will obtain in the next 2 hours is a PhD in astronomy and astrophysics. And while you might have an idea of what astronomy is, you might wonder what astrophysics actually means. And so the goal of an astrophysicist, me, is to describe and understand astronomical objects, astronomical phenomena, with essentially the same physical laws that apply here on Earth as well. And you can do that on all different scales. You can look at planets, you can look at stars, you can look at galaxies, and you can look at the universe as a whole. But my main interest is stars. And of these stars, what I would like to know are their general properties. For example, the size of the star. How massive is this star? What kind of temperature does it have at its surface and all the way in the inside of the star? How does it get born? How does it evolve? How does it die? And what kind of effect does it have on its environment? For example, stars are the main source of heavy elements in our universe. So, and by heavy, as an astrophysicist, I mean anything that's essentially not hydrogen and helium. So the things like carbon, iron, those are the products essentially of stellar evolution. So that's essentially my main interest, but that's not something you can just do like this. There are quite some challenges associated with it. And the first challenge is with regards to observations. When I speak about observations, typically what we mean by that is a telescope looking at the sky and making measurements. And that can be a telescope here on Earth, like the one shown here on the left. That's the Mercator telescope on La Palma, which is operated by KU Leuven. Or a telescope in space. That's artist impression on the right here of the TESS spacecraft that is operated by NASA. But when we look at stars, and this is where the challenges begin, the issue is that we only see the surface of the star. The atmosphere, essentially, of a star is opaque, so you can't see through it. And that means that when we observe a star, the direct information we get is only about the interior of the star. And on top of that, many stars are, well, almost all stars are far enough away that we cannot resolve their surface. So if you see this image here, and typically if you see such an image, that will be an image of the sun, because the sun is the only star that's close enough for us to make such images. For other stars, we typically just see the light, all this light bunched together. So you wouldn't see, for example, these sunspots that are shown here in this image. A second challenge is that stars live a very long time. And we only see them essentially at a single point in their life. So you can see the graph here. This is the life cycle of the sun. It was born approximately 4.6 billion years ago and will, let's say, the main part of its lifetime until it's become a white dwarf, that will end roughly around 11 billion years. So you can compare that with a human lifetime, that's basically nothing. These stars live so long that we can't, from looking at a single star at a single point in time, we don't really know where they're coming from and how they evolve. So observations alone, therefore, are not enough to fully understand stars. If observations are not good enough, maybe you want to look at theory or simulations. And unfortunately, these simulations have also challenges. So to give you an idea of what a simulation is, it's just some numerical description of a star in our computers. So I've shown here the T, which is symbol for temperature, and that depends on essentially the coordinates. So you have your R, which is the distance from the center of the star, and you have your theta and your phi, which you can roughly interpret as your longitude and latitude. And what we then do, if we have such a description of a star in our computers, is we add physics to that. We tell our computers how gravity works, keeping the star together. We tell it how nuclear reactions work. So in the core of the star, for example, on the main sequence, we have hydrogen being converted into helium, and that's the main energy source of a star. And teaching essentially the computer those physics allows it to change and evolve these properties, such as the temperature, over time. And so that way, we can see, in principle, how a star evolves from its birth until its death. However, again, stars live for a very long time. And so in order for this to be computationally feasible, we will need to make approximations, because even if you would combine all of the computational power in the world, we probably still wouldn't have good enough, let's say, compute to fully simulate a star from beginning to end with all possible details in the simulation. So instead, we need to make these approximations, and a typical approximation to make is that the star is one-dimensional. What do I mean by that? I mean essentially that this dependence on theta and phi, we ignore this. So if you would think about this, what this would mean for the Earth is that for the temperature, it would be everywhere the same on the surface of the Earth. You may still keep track of how the temperature changes with depth, but everywhere on the surface, the temperature would be the same. And so that's a typical approximation we make when computing stellar models. Now, that brings some issues with it, and I would like to highlight one of them, and that is convection. So when energy is generated in the core of certain stars, that energy is essentially transported out by vertical movement. So you have some warm bubble of gas moving upwards, and some cold bubble of gas moving downwards. And so that movement transports energy and also mixes the material together. But as you can see on this image here, and I've now realized that I wanted to turn the lights down so you all can see a bit better. There we go. So on this image, you see essentially all these this is a snapshot of what convection looks like. So the colors essentially indicate in which direction the fluid is moving. And so this is quite a chaotic movement, but also inherently three-dimensional. You have to be able to move things past each other in order to have this energy transport outwards away from the center of the star. That means, however, that in a one-dimensional simulation, we don't get that, right? You think about in a one-dimensional simulation, all these colors here, you should have from the distance to the center, they should just be a ring of the same color. And we don't see that here. And so we need to essentially emulate this effect of convection. So that means that emulate the energy transport, emulate the mixing of material. But because we're not running the full physics, we have some unknown parameters associated with that. And so that means if we want to do our one-dimensional simulations, these are not enough on their own because we have these unknown parameters. So neither observations nor theory and simulations can help us. So what do we need to do then? Well, it turns out that there is some hope. We can essentially combine both of them. If we start from observations, we can look and compare these with what theory and simulations predict and validate our theories and also calibrate those unknown parameters. And by doing that, we can learn something about the fundamental properties of the star, so its mass, its age, but also figure out how this underlying physics inside the star, such as convection, essentially operates. Now, what kind of observations am I talking about? Well, you may already know that from my thesis title. I'm talking about pulsating stars. So, what are pulsating stars? Pulsating stars essentially are stars which have waves that travel through them, and they combine into what we would call a global oscillation or a pulsation mode. And I can, let me see, yeah. So these are examples of how these pulsations would look in the star. This is a bit exaggerated. The movements are not that strong. Well, depends maybe a bit on the type of star, but for at least the stars I'm interested in, it's not this strong. And so essentially, what these movements do at the surface of the star is that it changes the temperature, because you can think of if gas expands, it cools down, and if gas compresses, it heats up. And because the temperature of a star essentially determines its luminosity, so how bright it is, these movements that change the temperature at the surface of the star will also change the brightness of the stars. So that's why these are pulsating stars. These are stars whose brightness changes over time. And we can essentially compare that to, so that's more or less comparable to, for example, an earthquake, right? So an earthquake is a wave traveling through the interior of the star. The main difference is that in a star, it's more like a continuous earthquake, right? Here on Earth, we have single events, essentially, while on a star, it's more essentially happening all of the time. And so that's also where the field that studies these pulsating stars, astroseismology, gets its name. This is the seismology of stars rather than Earth's. And you can also think of these pulsations and these stars essentially as musical instruments. So if you have some instrument and you play, it can, let's say, produce sounds at certain specific frequencies. So those are essentially the notes of your instrument. And for these stars, it's effectively the same. These pulsations that I showed can only occur for a specific star at certain frequencies. And that will essentially allow us to learn something about the internal structure of the star. But just like a musical instrument, if you listen to an instrument, it's not a pure tone. It's not, let's say, 440 hertz exactly. No, it's a spread of frequencies that makes up how the instrument sounds. And for a star, it's essentially the same. And you can see that a bit here in the plot on the left. This shows the time variation of a star I'll talk about in a bit. So the variation of the brightness. And you can see here that this is not, if this would be a single frequency, this would be a nice sine wave. But it seems like a whole bunch of mess on top of some overall variation. And that is the result of multiple frequencies being active at the same time. And typically, we can transform this plot here on the left to the plot on the right, which shows how much a star is pulsating in a certain frequency. So that's what these peaks here in this diagram, which we call a periodogram. That's what these peaks signal here, that there is a frequency in this star with a certain amplitude. And so just to temper the expectations a bit, this data here on the left is not enough to give you everything here on the right. This periodogram here, that you get that from at least a year of continuous observations of this specific star. And so a lot of information is available in these pulsations because essentially each peak probes the interior of the star a bit differently. And so you can, from certain peaks, you may get information about the outer layers of the star. From certain peaks, you may get information about the inner regions of the star. And so together, we can, in principle, from the pulsations, learn something about the entirety of the star. However, in order to do that, we need techniques, modeling techniques, to essentially make optimal use of this information, right? It's not that directly from these observations, I can just say, I know what the star is. No, I have to actually put in some work. And so what was the goal of my thesis? It's essentially to push the current modeling techniques we have as far as possible and try to extract as much information as possible about our star. And what I will do now, essentially, for the remainder of this presentation is focus on one specific star. And that specific star is called HD 192575. You may wonder why does it have that name? Well, there's just too many stars in the sky to all give them interesting names, so they end up having a number. What is interesting about this star is that it essentially has the richest frequency spectrum, so that means specifically in its class. So that means essentially that this star has in its frequency spectrum most information about how it looks on the inside. And what kind of things can we learn from this? Well, we can learn something about the internal structure of the star, so that by internal structure, what I mean is, for example, how does the temperature vary with depth? How does the density vary with depth? We can learn how fast the star is rotating, and whether, for example, the inner regions of the star are rotating at the same speed as the outer regions, or they're rotating faster or slower. And we can learn something about the magnetic field of this star, right? Because these stars, they do harbor magnetic field, and these leave an imprint on the pulsations, which we'll be able to analyze. So a bit more about this star. It is what we call a massive star. Those are stars essentially that at the end of their lives will die in a supernova explosion. And this specific one has roughly 12 times the mass of the sun. And its current age is estimated to be about 15 million years, although there are some uncertainties on that, which we would call the second half of the main sequence. So the main sequence is where the star burns hydrogen into helium in its core. And so it's in the second half of that part. As you can see, so the plot on the left here, so the brightness variations are up to 1%. And the pulsation frequencies, which are shown here, are on the order of a couple of oscillations per day. So that means if we would just look at one frequency, for example, the big one over here, that one has 7.5 oscillations per day. So over 2 days, it would have gone up and down 14 times. Now, you may wonder, okay, you have all these beautiful plots to show, Vincent, but where actually does this data come from? It did not, well, maybe it literally fell out of the sky, but no. So this star was observed by the Transiting Exoplanet Survey Satellite, in short, TESS. And that's a satellite, so it's in space. And you then might wonder, okay, why do you go to space? What's so useful about going to space? Well, two things. First of all, in space, we can continuously observe a certain region of the sky, because on Earth, we have to deal with the day-night cycle. So it loses roughly half of our observations. And there's also no atmosphere in the way. You might wonder, why is that relevant? Well, the atmosphere can distort the light we get from the star. And you can actually see that yourself. If at night you would look up at the stars, you see them twinkling. Well, that's not that these stars are pulsating. They might be, but that's not the main reason. The main reason is essentially the atmosphere is distorting the light, and that's what's causing these twinkles. And so it's better to not have this atmosphere in between us and the star at all, so that's why we go to space. And so yeah, I've shown this picture earlier. This is TESS. A bit more about how TESS observes the sky. So what it essentially does, every 2 years, it scans the entire sky. And so it essentially does one hemisphere per year. And it does that in blocks of 27 days, so roughly 1 month. And that is what we call a sector. And during that month, it fully measures the brightness of everything in that sector. So you can see that here. So this is such a segment here that's indicated here in blue. That's a sector. And so for 1 month, it will observe how the brightness of all the objects in that part of the sky varies. And you can see here as well, and maybe it's better in the plot on the right, that there are regions where these sectors overlap. And those are regions essentially where we then have a full year of coverage. So in this red region, and this is where our star AG192575 is actually located, we get a full year of measurements every 2 years. And so the fact that it revisits these regions every 2 years is going to be quite important, and that's why I'm going to put a pin in that, and we'll come back to that later. Yeah, and so why are we interested in a star in that region? Well, essentially, the longer you observe the brightness variations of a star, the better we can resolve frequencies that are very close together. So again, back to this plot of the frequency spectrum, or the periodogram. So here up top is the same plot essentially I've shown before, but on the bottom here, I have shown zoom-ins on specific regions, right? So these purple boxes, you maybe not be able to properly see the one here, but those correspond to the 3 boxes here below. And so the left one here corresponds here, and we have the 2 middle ones. And what you may have noticed by looking at these plots is that you see that these frequencies here that show peaks are somewhat equally spaced, right? So this distance, and this distance are roughly the same. Now, you may wonder, why is that? And that is what's going to lead us to understand the internal rotation of this star. So let's have a look at how that actually works. So how does rotation affect the pulsations? Right. So these are pulsation modes. I've shown these ones before, but these ones are slightly simpler animation of that. And you can see, first focus on the top row, those are pulsations in a non-rotating star. And you can see there's essentially 3 variants, but they all have one white line. And so that white line indicates where there is no movement due to the pulsation. And so in a non-rotating star, or a star that is spherically symmetric, the orientation of that white line shouldn't have an effect on the frequency. And so that's, if you look at those plots there on top, if you look at the left, middle one, and right one, you see that they have the same frequency. If you, for example, follow, let's say, the red region, you will see that it will appear at the exact same location for all of them at the same time. Now, imagine you take those top ones, and you now add rotation to that. So essentially, you rotate the star like this, right? Then the left one should slow down, because it was moving opposite of now the stellar rotation. For the middle one, it doesn't matter, right? If you start rotating that one, nothing changes. And for the right one, you see that it accelerates, right? well, it has accelerated compared to the top one, and so it's moving faster. And so if you now look at the frequencies, you would see that this right one has a higher frequency, the middle one has the same frequency, and the left one has a lower frequency. And so that's essentially what rotation does. It gives you, starting from no rotation, it goes to a splitting in frequencies because a certain mode goes faster, a certain mode goes slower due to the rotation. And it depends a bit on the type of mode that's indicated by this letter L. And that counts how many of those white lines you have at the surface. So if I go back to these, the single white line here, that means it's an L equals 1 mode. And so this L equals 1 mode corresponds to, okay, we go from 1 frequency to 2L plus 1 frequencies, so to 3 frequencies. And for an L equals 2, we go from 1 frequency to 5 frequencies, and so forth, right? But typically, we don't see modes with higher degrees than L equals 2, L equals 3, mainly because if you have all of those lines on your surface, you're essentially subdividing your surface more, and the integrated effect of all those hotter and colder, or brighter and dimmer regions, that average out closer to 0. So we typically, for stars except for our sun, where we can resolve the surface, we only see L equals 1, L equals 2. Now, since that explains what these multiplets are, but that also means that rotation, since it affects your pulsations, you can go the opposite way around and learn something about rotation from your pulsations, from these, what we call a multiplet. So a group of those frequencies would call a multiplet. But I'll, again, come back to that. I've shown these multiplets here as being symmetric, but certain effects can also make them asymmetric. And again, that's something we'll have to come back to later. Okay, so now we understand essentially a bit more about this frequency spectrum. Because now we know that these mode, for example, with its equal splitting, that's probably from rotation, and it would at least need to be an L equals 2 mode, because you have more than 3 frequencies. The ones here on the right, they can be L equals 1. And the ones here on the left, they must again be L equals 2. And so that's already something we can learn from just looking at the frequency spectrum. So now that we have this frequency spectrum, what do we do with this? Well, the first step, if we want to learn about the internal structure of the star, is what we'd call forward modeling. But maybe a better way to understand this concept is to think of it as evolutionary modeling. This means that we have some initial parameters for the star, such as the mass of the star, the initial mass of the star, the initial composition of the star, and a range of tuning parameters. For example, that unknown parameter I talked about with regards to convection, that's something you can also include as a free parameter in, well, you can include a range of those parameters in your forward modeling. And so what you do for every combination of parameters, you start a model from the, let's say, the beginning of the life of the star and run it, well, typically in our case, we might run it until the end of the main sequence when all the hydrogen has been converted into helium, because we already know from some other information that that's most likely where the star is in its life. And so if we have such a simulation, we can, from that simulation, compute what frequencies we expect the star to oscillate in. And so in the plot on the left, I'll explain step by step what this actually shows. So on the x-axis, it shows essentially the age of the star, with the star being younger on the left and older on the right. It is measured here in how much hydrogen is left in the core of the star. And on the y-axis, it's the frequency. So think of that periodogram that I showed earlier, just tilted now, essentially. And these horizontal lines here, those are the observed frequencies. And the symbols, like for example, this set of blue symbols here, that's what we get from consecutive models for a given set of initial parameters. And what we essentially do is we compare these two, and we see, for example, for this model, that most likely it will fall, that the real star would fall in this shaded region. That's where the observed frequencies more or less coincide with the modeled frequencies. We don't do that just for one range, so for one simulation, but for a whole bunch of simulations for all our initial parameters. and then we compare that with observations, and we figure out how these, for which models, these observations more or less match what the models predict. And then you can say, for example, here in the results on the right, okay, the initial mass of my star is somewhere between 10.5 times the mass of the sun and 13.5 times the mass of the sun. And similarly, you have the result for the age of the star here, and you can see that it's indeed roughly 15 million years. But again, there is some variation on that. And that's something you always have to deal with, essentially, in science. You will not be able to exactly say, okay, this is my correct model, the star is doing exactly this. There will always be some uncertainty. Of course, the goal is to get that uncertainty as small as possible, but it is there, and we need to report on it. Now, going back to the low-frequency multiplet, and this is where test revisits this star every 2 years will become important. So by the low-frequency one, I mean this blue and orange lines here. So that's essentially this multiplet here. So that was the one that was highlighted in the bottom left when I showed the full frequency spectrum. And so what you may notice about this frequency spectrum is that these frequencies, there are some that are very close together, right? And that means you need to have long enough observations to be able to tell them apart. And initially, if you have the one here on the right, that's indicated with the orange one and the blue two. So the blue two, are, after the first year's observations, that was not a significant peak. But after more observations, we found that it was significant. And essentially what that did is, that required us to push these two, this blue frequency here and this orange frequency closer together. Now, that wasn't really possible in the models that we computed, and so the conclusion essentially we had from this modeling was that it was not possible to explain this multiplet just with two multiplets very close together. So what we did with that is we essentially, in the first place, ignored it. In the sense, we said we cannot explain this yet. Let's just consider it one multiplet. Now, that's not really proper in the sense that you do still want to explain that. Luckily, we managed to do that. But again, we'll come back to that later. So if you're keeping track now, there's a bunch of things I need to come back to. But luckily, I can immediately come back to one of them. So now that we have an understanding of how this star looks on the inside, so we know something about its internal temperature, its internal density, we can go one step further and now try to figure out how does the rotation profile inside the star look. And for that, we'll use a second modeling technique that is called inverse modeling. And maybe another name for this would be point-in-time modeling. So rather than starting from initial conditions and evolving a simulation up until the point where the star currently is, we are just going to figure out what is currently the rotation profile without requiring that there is some simulation that will give us that rotation profile. And that's, I've shown here an example on the bottom right. That's, let's say the structure of our Earth, and essentially what, for example, geologists do to figure out how, from earthquakes, how does this Earth look on the inside. And that's essentially also where we got, as seismologists, a lot of the techniques that we still use today to do this inverse modeling. Now, this has some advantages. It allows us to explore more physics. So, for example, understanding the internal rotation of a star, if you want to do that with simulations, we are not there yet. We don't have enough understanding of how rotation and angular momentum transport works inside these stars to actually be able to model, so to match observations and our simulations for the case of rotation. So that's why we just look at how is the rotation profile now and not do these evolutionary simulations. Now, a second benefit of inverse modeling is it also can tell you at which point in the star your model might be wrong. So you might have some mismatch between your stellar model and your observations. And you can essentially calculate back to see where in the star your models might be wrong and how much they are wrong. And that can help you understand how you should tweak your stellar models to better match the observations. Now, that is a bit of a disadvantage in the sense that you have more freedom because you don't have that constraint from the evolutionary history. So that might give you a bit more uncertainty on your results. And it does not answer why the star is currently doing what it's doing, because you don't have that evolutionary explanation anymore. So we did a rotation inversion for the star. So that essentially means we took our rotationally split multiplet, and from that derived what the rotation profile of this star could be. And so looking at this figure here in the bottom, what essentially shows on the y-axis you have the rotation frequency at essentially various depths inside the star. So 0 here all the way on the left, that is the center of the star, and 1 here on the right, that's the surface of the star. And each of those lines here essentially is a possible rotation profile for this star. So I've talked about that when we do our forward modeling, we have some uncertainty on parameters. Well, that uncertainty essentially propagated into the fact that we have multiple rotation profiles here. So we have multiple possible evolutionary models that give us something that more or less matches the observations, and each of those models has an associated rotation profile. And that's the variation you see here. This is a subset of them, but this shows more or less how they vary. What you see here as well, well, you might not call this weak differential rotation, but that's what we would call it. So by that I mean if you look at the rotation rate close to the surface of the star and the rotation rate more or less close to the center of the star, let's say they are at most a factor 2 difference. And that's what we would call weak differential rotation. But even with all of this variation, we can still make an important conclusion, is that with our current star models and the observational data, we don't have any monotonic profiles. So a monotonic profile is essentially the red one shown here. That's a profile that doesn't go up and down, it only goes in one direction. So this one continuously goes down. In principle, you could also have one that continuously goes up. And that is in conflict with 2D simulations. This red line is a result from a 2-dimensional simulation. And so that either means something is missing in the 2D simulations or something is missing in my 1D simulations. And it's probably a bit of both. So that's essentially what we got for the rotation profiles of this star. And then from those rotation profiles, we also looked at the multiplet asymmetries. So remember when I told you that rotation splits one frequency into multiple frequencies, and in a simple, what we'd call a first order approximation, that gives you symmetric multiplets. Now, if you include more effects and go to a second order approximation, these multiplets will become asymmetric. And a cause of that, so one of the reasons that these multiplets become asymmetric is stellar deformation. So when you rotate a star, you have a centrifugal acceleration, which is stronger at the equator than at the poles. So your star essentially will become a bit oblate. And you can see that here in this picture. So these stars are no longer spheres, they're oblate spheroids. And so this is the case for very fast rotating stars. For my star, AG192575, the difference in radius between the equator and the pole is only 1%. But that still has a strong effect on the pulsation frequencies. And you can see an example here. So this plot here shows how do the frequencies change as you increase rotation. And you can already see at the beginning, you have a single frequency that splits into multiple. That's what we explained as this, these rotational multiplets. But if there was no deformation, that splitting would be symmetric and continue on these straight lines here. But you see that that is not the case, right? That they are deviating from that, and you see that this one, for example, is these two are much closer together than these two. And that's the asymmetry I'm talking about. There's also some interesting effect where if you look at this orange one, this is an L equals 0 mode, so it doesn't split up when rotation is present in the star, but it can still change. And specifically, for example, this L equals 0 is also interacting with this line here from the L equals 2. So they're essentially pushing each other apart. And for the star, for my star, AG192575, that is an important effect, and we need to include it. Now, the issue with that is that if if we want to know these frequencies from our models, we need to have software to do these computations. And while there exists software to do computations of pulsation frequencies, there exists software that can do these higher orders effects of rotation, and there's also publicly available software to do that. There wasn't any publicly available software that allows us to compute these from non-rotating base stellar models, and that allows to do this coupling that I showed between this L equals 0 and L equals 2 mode. And so that's why I had to write my own oscillation code, which is called STORM, which stands for Stellar Oscillations with Rotation and Magnetism, although the magnetism is still not yet implemented. But the name was cool enough that I thought, let's keep it in for now. But with this code, I computed the asymmetries for our multiplets, and this just shows one of them. And we found that the computed asymmetries were not inconsistent with observations. And you can see that here. So these orange boxes show all the potential asymmetries that the models give, and the blue vertical lines show the observations. And you can see, at least for these ones on the left here, that the observations fall in the range of the models. Not quite here for the ones on the right, but essentially we only need to have one stellar model in principle that explains our observations. But in order to fully, in order to do that properly, what we need to do is a combined fit of all of these things. Because the way I have currently explained it is we started with deriving the basic properties of the star. Then we went on in a next step to derive the rotation profile. Then in another next step, we looked at the asymmetries. But ideally, you could combine all of those things together into one, essentially fit, one step that optimizes for all of these parameters. And so one of the reasons to do that essentially is because there may be some assumptions that you made in your first or second step that may not be right to do the analysis for the later steps. So yeah, that's what this shows here. All right. So at this point, we have only one more thing to return to, and that was this lower left, this lower frequency multiplet, where we said, okay, we can not explain this as two multiplets. It has to be one multiplet, but we can't just have that with rotation alone. And so to explain this multiplet, this is work I did with a master student, Jelle, who is sitting right there in the room. And so essentially what we figured out together is that this multiplet is caused by magnetism. So what magnetism can do is it can give you additional frequencies in your multiplets, as long as, if you look at your rotation axis and your magnetic field axis, that those have an angle between them. And if we observe such a multiplet, we could learn about, well, we know we can learn about rotation frequency. We could learn about the magnetic field strength in this star, the angle between the rotation axis and the magnetic field axis, which we call the obliquity, and the inclination axis, the inclination angle between the rotation axis and the line of sight. And so these are all the properties essentially we could derive from such a multiplet. And it turns out, indeed, we can explain this multiplet with magnetism. So the blue dots here show what the best model is, and the orange symbols are the observations. And you can see that those more or less match. There is one blue dot here down below, but that's probably because the noise level of the observations is too high to actually observe it. And there is some small difference here on the right. But overall, this is essentially, for this type of star, this is the first time that this kind of analysis has been done. And I already learned us something about the magnetic field of this star. So, to recap, well, I should get some water first. So, in order to understand how stars work, we need to combine observations and theory and modeling and simulations. And for that, we needed more advanced modeling techniques. That essentially, I would say, even going beyond this thesis, we are still not there yet. There's still more work that we need to do. So what did this thesis do? We pushed the techniques we had currently basically as far as they could go to these beautiful pulsating stars. And we looked at a specific case study, namely the star HG1925775, and we found that its rotation profile cannot be monotonic, at least with the current models that we have. So those were the ones here shown on the right. We found that while we can, let's say, somewhat explain the asymmetries, the observed asymmetries, we need combined modeling for all sorts of different properties of the star to actually understand what's going on. And we found that the low-frequency multiplet in this star was explainable by a combination of rotation and a magnetic field. And so that's where I'll leave you with my presentation. And then it's now time, I guess, for the jury to grill me.
First of all, thank you, Vincent, for this very nice and lively presentation, which was very interesting. Indeed, the grilling will now start.
Excellent.
And so I first would like to give the floor to Professor Townsend.
Thank you very much, and thank you, Vincent, for a lovely presentation. Vincent, you primarily know me as someone who writes pulsation codes.
Yes.
But I had a prior life where I worked on magnetic massive stars. I'm kind of interested in the magnetic field of this star. Do you have a constraint on the sort of field strength?
Yes. I cut out some slides because of time, but good that I kept them. So yes, we do have some constraint on the magnetic field strength. So the plot here on the right shows, well, the potential range of magnetic field strengths we have, and I think this is given by the maximum point. If not, yellow can yell at me if I'm wrong. But yeah, so you see that so each of these colors is a different mode identification. And you can see that while we have some constraints, right, it's on, let's say, the main peaks here on the order of tens of kilogauss to hundreds of kilogauss, there's still quite some uncertainty that we would need to resolve to really say we have a proper measurement, I would say, of this magnetic field.
Do you think there's any chance for a direct measurement of the field using spectropolarimetry?
So if I remember correctly, that's something we do need to look into a bit more detail. But I believe that is just possible. I think so. Let me think. The V-band magnitude is, I think, 6.8, and I think that was still possible to at least get some constraints. So that would be a very interesting follow-up from this work to try to get a spectropolarimetry and get a surface field measurement.
Indeed, yeah. Okay, so I'm going to go back to a nice analogy you made earlier on in your talk to the fact that stellar oscillations, there's a nice analogy with musical instruments. Mm-hmm. So with stellar oscillations, who plays the instrument? Why do these stars oscillate?
So there are multiple reasons why these stars can oscillate. It depends a bit on the type of pulsator. For the star that I talked about, it's what we call the kappa mechanism, which essentially means that there is a layer somewhat close to the surface of the star where you have a bump in the opacity, and it acts like a heat engine. So for everyone else in the room, it's essentially a layer that continuously expands and contracts due to the, let's say, the radiation field in the star. And that continuous expanding and contraction that causes waves to travel inside the star, and the ones that survive, that don't cancel themselves out, those are the ones we then see as the pulsation modes of this star.
Okay, and what about other types of stars?
Yes.
Let's say the sun.
So another possibility is if you have, so I showed this convection earlier, and so when you have, when you have convection inside a star, for the sun that's in the surface layer, so let me just go back to an example. So when you have this boundary here between the convection zone, in this case the convection zone, and the outer layers, there is quite some movement here that happens. And that pushes against the material, and that also sends waves through the star. And you can see those are those like red regions, blue regions here that you still see. And those waves can also excite oscillations. That's not necessarily for this star, because it's not the sun. The sun does not have a convective core, but it has a convective outer layer, and that can essentially do the same. So that's a sort of continuous movement through the convection that pushes energy into the pulsations.
Okay, thank you. So remaining on the theme of convection, for the sorts of stars you're interested in, we know that most of the convection is in the core, as this image shows, but we know that based on new opacity data in the 90s, it was recognized that there can be subsurface convection zones driven by the same ion bump that's actually responsible for exciting the pulsations. We know that the interaction between pulsation and convection is important in understanding gamma Dor stars. Do you think it will be necessary at some point to include pulsation-convection coupling for beta Cephei stars?
Maybe, I would say, at this point, maybe not yet. Perhaps it's more interesting if you're also going to look at excitation of the modes. Then you might need that. In terms of the frequencies, I would say it's hard to say because there's still a lot of other issues we're dealing with that I think we need to solve first before I guess that becomes important.
So do you have any plans to put excitation physics into STORM? Does that come after magnetism, so it's STORM with an E on the end, Stormy?
To be fair, that's a good name. I should keep that in mind. No, I think so. First of all, I think magnetism will be the first focus. So that's where we go first. And then, yeah, it's still something, well, you know, I wouldn't mind bringing my code up to parity with Gyre for a whole bunch of things. So at some point, that will probably be on the table to include all the excitation mechanisms.
Okay. One final question before I pass the mic over. In your simulations, you fixed the envelope. This is a very technical and boring question, but you fixed the envelope diffusivity to 10 to the 3 centimeters squared per second. Can you motivate that choice a little bit?
I think this number, if I remember correctly, came from what we sort of expect the, let's say, the mixing floor to be due to, well, essentially these types of waves. So these are internal gravity waves. And so they move through the star and they can induce some mixing. And I believe that's where it was calibrated at. But these were simulations that I used that essentially build up from previous work from a previous PhD student here, Simon Bersens. So I used all of his work for that. So I'm not 100% familiar with those details, but if I remember correctly, that was the reason.
Okay, thank you. Shall I just pass the mic over now? So to Professor Christensen Dalsgaard.
Thank you very much, and thank you also from me, Vincent, for a very nice talk, but also for a very nice thesis. I really enjoyed reading it. I made a lot of red marks in the first version, but I'm looking forward to making red marks in the next version. but it's really a very impressive project you've carried out here, and very wide-ranging, both in terms of data analysis and computing and coding. So we learned a lot about stars from this, but I'm also a bit worried. You presented, you may go back to that, a plot of the rotation rate in the star.
Yes.
Also, you had that in your summary slide.
It's going to be here somewhere. Yeah, there we go.
So what is the star really doing? And how are you going to decide eventually what the star is really doing?
Yes, so there are two routes essentially we can take for this, and probably we'll end up doing both of them. So I don't think so some of this variation came from uncertainties we had during our forward modeling step. And I think there we haven't fully exploited all, well, we haven't 100% done all the necessary statistics. And I think we can get some improvement there and get just a better constraint on our sterile models to begin with, and that will already reduce the number of profiles. I would say there's also some profiles that are probably not physical. So, for example, the one here that goes, well, that falls off the plot essentially. That one is probably not physical, so we can probably make some cutoff there. There's some interesting input as well from three-dimensional simulations that can give us potential rotation profiles, and that we maybe also be able to use as a constraint to hopefully better understand what's going on.
So basically, these are all different models of the internal structure of the star.
Yes.
And so it's a way that you can use some idea about rotation to constrain the models of the structure and combine the inversion for the rotation and the inversion for the structure.
Yes.
And there's also the mode identification going into all this, of course.
Yes. Yes. That should all, in my opinion, be combined into one modeling step, so to say. Well, it might be easy standing up here to say those things. I think there will be quite a bit of work to actually get that done. But I think that's going to be necessary at some point to do it.
Right. Now, if one of these rotation curves were right, and it's correct that it's not monotonic, is there any good physical reason why you can get rotation looking like that in a star?
Yeah. So for that, I'm going to come back to the internal gravity waves. And so we do find in 3D simulations that have internal gravity waves and magnetic fields that you can set up a profile that does have a non-monotonic behavior, so that maybe begins a bit like this, goes down, and then goes back up. So that's, funnily enough, something I learned this week, talking with some of the people that do these simulations. But yeah, so that's so the angular momentum transport by internal gravity waves may be one of the reasons for why we have these varying profiles.
Right. Okay. So we can actually learn about the transport processes from this. Are there other kinds of transport processes that are important in the star?
You mean specifically for rotation or in general?
In any kind of things moving about.
Yeah. So yeah, there are a bunch of transport processes. So in principle, convection is one of them already. Mm-hmm. So that happens for this star in the core. And that's very efficient at mixing material. There's, you can also separately look at how this transition goes from the convection region to the radiative region, and we still don't know exactly how that's supposed to happen. There's also effects if you look at specific elements from the radiation. You may also get certain types of elements that move up inside the star through radiative levitation. And probably the presence of a magnetic field. And, well, yeah, so presence of a magnetic field may also potentially induce instabilities, which can then mix material and cause transport that way as well.
Yeah, okay. So how would you study this motion of elements in the star?
So there has been, I think the main promising aspect, well, we have looked at this, not for this type of star, I believe, but we have looked at this. And one of the things it affects is the excitation mechanisms. So this iron opacity bump, for example, how strong probably depends on what kind of elements are in this region. And so if you have radiative levitation that moves elements around in the star, you may change which oscillation modes are essentially excited. And so, if I remember correctly, we have done certain calculations for that and found that indeed we do need these kind of effects to have a better match between the observations and the models.
I was thinking more of whether you can think of any other observations that might be useful in studying the composition of the star.
So I think it's, so I haven't talked, for example, about spectroscopy yet.
Yes.
So spectroscopy is essentially when you look, when you have light from a star, you can split it into its frequencies. and certain dips correspond to certain elements. And so that can help you constrain, well, some global properties of the star, such as the surface gravity, but also what kind of elements are present in the surface of the star. So that could, for example, be coupled with these, with radiative levitation. So we have photometry. As Rich already essentially asked about, the spectral polarimetry that can learn anything about magnetic fields. When we have these stars in binaries, we also have additional constraints. Since these, well, when you have binaries, because you learn something about how these orbit around each other, you can essentially learn something about the masses and the radii involved. And that can also be already a constraint on your star.
Right. Now, to go back to the magnetic field, it's very, very interesting that you found this. Why does a star have a magnetic field?
So essentially, when typically throughout our galaxies, there are already magnetic fields. Essentially, you have charged particles moving around, and those can cause magnetic fields. And so when a gas cloud that will become the star, when that has magnetic fields in it, when it collapses, essentially pulls the magnetic fields together and forms and produces a magnetic field inside your star. That's what we'd call a fossil field. And a second aspect is that if you already have some seed magnetic field, the rotation and the convection can cause a dynamo to occur. So, and that just strengthens up your magnetic field, and that's then the second cause of magnetic field would be a dynamo field.
So do you want to guess what's causing the field in your star?
I don't think I want to guess, in the sense that at this point we've just tested one field topology, and in order to actually know whether it is a dynamo generated field, whether instead of just a, let's say, a current dipolar or fossil field, we would have to test more magnetic field topologies, but that's something we do intend to do in the future.
Right, thank you. Well, I could go on. I could ask you to explain to me what the Mahalanobis technique is, but since you're using it, do you want to have a go at that in simple terms?
Sure. So essentially, so when we are comparing frequencies with observations, we always have some observational uncertainty on our frequencies, right? There's some limitation in the observations. And so we use a specific measure, which is called a chi-squared, typically to have a single number that describes, based on those observational uncertainties, how good our stellar model fits. So that's the simplest case, and then we assume that there is no correlations between our frequencies. What that means when you have a correlation is that, let's say, if you have some frequencies that are uncertain, so they could be anywhere, when you have a correlation between two of them, you expect that, for example, if one of them is slightly more to the right, the other one should also be, or opposite, maybe it's more to the left, but they are correlated. So the Mahalanobis distance takes that into account. But we go one step further. We also take into account that there is some uncertainty in our stellar models. Because I've talked about these 1D models, that they can't describe everything, and we do have some prescriptions to include certain effects like convection, but those are not necessarily correct. And there may be physics that we are not including in our models that do happen in the real star, and that cause additionally a mismatch between the observations and our modeling. And so what let's say the extended version of the Mahalanobis distance that we use, what that does is it tries to account for that.
Thank you. We need to talk.
Yes.
I think I have to give up here and pass it on to the next.
Professor von Holst is next.
Thank you. Well, Vincent, thank you first for a very lucid and entertaining presentation, I would say. And thank you also for your work, which is very profound, I think, very ambitious. Let me maybe start like Professor Townsend started. You probably know me as a planetary scientist. But before, I also worked in astroseismology and nonlinear astroseismology. So can nonlinear effects play a role in your work?
Yes. So in the first place, as for these type of stars, let me just grab a frequency spectrum. Yeah, so for example, this one. These heights of these peaks, these amplitudes, when we do our normal calculations, they are not determined. And so what you can get from doing nonlinear astroseismology is you can start computing these amplitudes. So essentially by, yes, now I remember what I wanted to say. For these type of stars, the height of the peak is essentially determined by coupling, nonlinear couplings with itself and with other peaks. And so that could, if we were able to properly do those calculations, we're working on them. I don't think we're necessarily at the point where we can fully apply that to a whole bunch of stars. There's still more work to be done, I believe. But yeah, that could be an additional constraint, right? If you expect some peak to be there, but it isn't, or you see a peak that you don't expect to be there, you know that something is wrong in your modeling. And so that could help here. A secondary effect is that these nonlinear couplings can also change the frequencies. And especially in these rotationally split multiplets, when I look at the asymmetries, if you have nonlinear couplings between different components of your multiplet, they can essentially remove some of the asymmetry. And that could also be an important effect to take into account, but you would need to do some tests to see whether that is actually currently the case, looking at the phases and such of the pulsations to see where that's actually going on.
Okay, thank you. As I said, I think your thesis is very ambitious, and your future plans are even more ambitious, I think. So you want to include quite a lot of physical phenomena. You want to go to 2D and 3D modeling. I think several of these effects might be large, but some of them are clearly smaller. Did you make some order of magnitudes, back of the envelope calculations of what you think you should include first?
I guess that depends a bit on what you want to achieve. So, for example, if we want to look at, understand, for example, how the rotation profiles we get out of these stars currently are, for that, I would say it's quite important to have at least two-dimensional, but probably also three-dimensional simulation, to actually see that what we are doing in those one-dimensional models, whether that actually is the right thing to do. And at least in the current version of the one-dimensional code that I use, that's not the case, right? So we have clearly learned from two-dimensional simulations and two-dimensional theory that there are some effects that we are missing. So I would say that's an important one, having a better look at rotation. So I think that would be let's say the first thing in terms of higher dimensional simulations that would need to be included. Of course, at some point you can also look at magnetic fields, but I think we're there a bit more uncertain. So that would be a later step, I would say, than the rotation. So that would be the first focus, in my opinion, is to go for validating the rotation. Yeah.
Isn't there also a risk that if you make a more complex model, that in fact such more complex models could also, in a certain sense, blur your vision on it, because you have more degrees of freedom, so you have more possibilities for finding a good solution, but so I think there are limits to what you can do. Yeah. What do you think about that?
I think part of going to higher dimensions is not necessarily that. Part of that is actually trying to reduce the complexity of the model, right? Because in our one-dimensional models, we need to parameterize a whole bunch of things that may be naturally included in a two-dimensional system. So in effect, going to higher dimensional simulations may actually help you to reduce the complexity of your model, even though it would take more work to actually do the simulation.
Okay. A last thing related to this is there enough information, in fact, in the set of oscillation frequencies that you have to constrain all these properties that you might want to include in your model?
If you would just look at one star, probably not. This is essentially the star I showed today is the best case, and we still there have limitations, right? We only had 3 or 4 rotationally split multiplets. you can't get a very detailed rotation profile out of that. But what you could do instead is, rather than, in the end, the same physics should happen in all stars, right? It's the same laws of physics apply to all of them. So in principle, that also means that if you would look at a whole bunch of stars combined, you could use the constraint of all of these stars to together get a better understanding, right? So where you couldn't do that for a single star, you may be able to do that for an ensemble of stars.
Okay. In the case of the Earth, for example, we have seismology, which was the first seismology, let's say. Even there, we need to have other quantities to really build a 3D picture of the Earth itself. So what could you consider as additional quantities for stars, for example, to do so? For example, we use for planets, for example, tides, not only the basic oscillations, but tidal motions.
Yep.
We use a magnetic field, which we can observe, of course. Stars, planets in our solar system are closer by than stars. So what do you think we could use in addition to your oscillation modes?
Yeah, so I would say, well, I already partially mentioned that, so there's spectroscopy, which gives you more constraints on the surface properties of the star. Binary modeling, and then not only just to get out, for example, the radius and the mass of the star, but also look at how the orbit changes over time, for example. So that's essentially your tides, but then for two stars. And that also depends on, for example, the density distributions inside these stars. So that could be a potential alternative constraint. Maybe there's also some aspect in looking at how the stars, like, again, looking at population samples, for example, what kind of, let's say, if you have how many stars, let's say, become white dwarfs, and what are the mass of those white dwarfs? Can you compute back from that and get constraints in that way? So I think it's not, pulsations on their own will not bring you all the information. They will bring you quite a bit there, and yeah, there's still quite a bunch of other types of information we could still use. Specifically for this star, so spectroscopy has been used in the forward modeling. That's part of the constraint. It's unfortunately not in a binary, as far as we know. But yeah.
One final question about your code. In planets, we have codes developed specifically for planets to calculate oscillation modes. For terrestrial planets, it's of course quite different from what you're doing, but I'm also interested in calculating oscillation modes of Jupiter, for example, a gas giant, so very similar to a star in a certain sense. So my question is, can we use your code to calculate oscillation modes of Jupiter, a fastly rotating object in 10 hours, so flattened? And a related question is, we are interested in knowing what is the dissipation associated with such an oscillation. So we normally consider the viscosity. Is that something that you can do in your code?
So for purely the pulsation frequencies, you would be able to do it. Of course, you say it's a fast rotator, so we'd have to test to see whether the approximations that STORM makes still hold at the rotation speed of Jupiter. So that's one aspect. In terms of diffusivity, I think STORM is still a linear code. So we don't track how the modes, like all the damping and driving mechanisms, that's not in there. So in that sense, that would be something that would need to be added before you would get out those types of results.
Okay, thank you.
Okay, thank you. Well, Vincent, you know that also Professor Tom van Doorselaeren is a member of your examination committee.
Yes.
He cannot be here today, but he still has a sort of virtual presence because he sent me some questions to ask you.
Very good.
So perhaps I will actually start with the third one because I think it's a little bit connected also to the last question of Professor van Holst. And so the question is, you have considered how the rotation changes as a function of depth. In the solar case, we know that the rotation speed is also dependent on latitude. how would you incorporate that in the model?
So I would say for this star, for the model that we currently have, I would say that's almost impossible, in the sense that I don't think we have enough observational constraints to actually get that information out, because that's an additional degree of freedom that your rotation profile would have, and yeah, we have only 3 or 4 essentially data points, and so adding that degree of freedom, I don't think will give you better results, even though that variation might still be there.
Okay, thank you. Related to your chapter 2 in your thesis, the question is, the studied star is a special one, given that it is the only one that rotates sufficiently slowly. If it is that unique, then the question is, why is it necessary to model especially this star? Is it not better to try to understand a larger class of stars?
So I think you can look at it in 2 ways. So of course, for, let's say, a larger set of stars, maybe modeling this specific star is not the best choice. Maybe there is a more representative star, although that depends on the observations that are available and such. But on the other hand, the fact that it is a special star makes it also very interesting, I think, to study. And I'm not necessarily in this game to get the most useful result out, but also to get results out that I'm personally interested in. And I think the fact that this is a bit of a weird star, that makes it interesting to me.
All right, thank you. And then a final question that is related to chapter 3 of your thesis. And the question is, you match the frequency spectrum by adjusting stellar models. Is it also possible to use the light curves as an optimization target? And then the question is would that possibly be more robust than the frequency spectrum?
I think the issue with that is that the problem is that we can't reproduce the full frequency spectrum. We can't, so this, if you look at something like this on top here, we can't just simply start from our model and get something out that matches that.
Mm-hmm.
And I think if you'd want to match the actual brightness variation, you would need to get a much better match with your frequency spectrum. We only take a handful of frequencies out of here that we think we can do something with and compare those 2 models. And we don't necessarily produce the whole frequency spectrum.
All right, thank you. Does the promoter have any questions left at this point? No. All right, then as promised, I will turn towards the public. Is there anybody with a burning question?
It is allowed.
Yeah, you were first. Please speak up. And are there people online?
Yes.
Yeah, then you can repeat the question.
I'll repeat the question.
Please go ahead. Mm-hmm.
So the question is essentially, what does this R-star seismology mean? I think it's, so it is the radius of the star we get from our fitted stellar models. I presume the reason this was indicated like this here in this table is to like differ it from, let's say, a radius derived from spectroscopy combined with Gaia, for example. I presume that's the main reason why this was indicated here.
All right. I thought I saw a question there. Yes, please go ahead.
Knowing you, there was no way you called that star in the alphanumeric, so what was your nickname for it?
Oh, so the question is whether I have a nickname for this star. So I wouldn't say we have a nickname for it, but typically when we talk about stars, to not continuously say the numbers, we refer to the person that has studied this star. So this original was Siemens star, or Siemens-Burson star. Then it became my star, and now it's also Yellow star. So I guess that those are the nicknames that the star has.
All right. Other questions? Yes, please.
Vincent, when you started out on this work, you said that there was no publicly available software to do what you wanted to do. Is there now?
So the question is that, so I said here during one of, here, that there was no publicly available code that could do all of those things. And the question was, is there one now? Not yet. Hopefully, somewhere in the next few weeks, my code will become publicly available. And then there is a publicly available code that can do this.
All right, thank you. Other questions? Yes, please.
Recently there was an observation of, if I remember well, I don't remember all the details, I saw the main headlines, there was a supernova explosion where they could actually observe with spectroscopy the different shells of the nuclear reactions. Could this be in retrospect, because then we're talking about the end of the life of the star, could this be fed back into what you were doing, or is there no relationship at all?
I presume that there is somewhat a... Oh yes, the question, yes. Yep. So there's been recent news about observation of supernova where they looked at in a bit more detail the specific elements at specific shells. I would say yes, there is. So the question was, can that help with my modeling? I would say we can at least probably validate that to some level, because I would presume that the structure of the explosion has an imprint of the structure of the star. And so that, in principle, if you would compute that all the way back, maybe you get something out of that. But I would say that runs into a lot of issues because, let's say, we can do supernova explosions to a certain level. We can simulate those. But I don't know whether whether all the kinks in those simulations, all the uncertainties in those simulations have been worked out enough for us to be able to do such a comparison.
All right, thank you. Is there a final question? No? That means that all the rest is crystal clear. And that also means that time has come for the members of the examination committee to have deliberation. So please stay here and we will be back in a short while. Thank you. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee, appointed for granting the doctoral degree in science, astronomy, and astrophysics. Vincent Vanlaer has presented to the faculty the PhD thesis on the topic Structure and Internal Rotation of Pulsating Stars, impartial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics. And Vincent Vanlaer has defended this thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Vincent Vanlaer the degree of Doctor in Science, Astronomy and Astrophysics. By obtaining the doctoral degree, Vincent, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity, as described in the ALEA European Code of Conduct: reliability, honesty, respect, and accountability. With that, I close the session, and a warm congratulations. All right. So, ladies and gentlemen, this concludes the formal part of this session. Please take a seat. And I'm going to give the floor to Professor Aerts for some words.
Thank you. I'm so tiny that I will climb up the stairs to address dear Dr. Vincent. Woo! Doesn't that sound nice? Van harte gefeliciteerd, Vincent, met je doctoraat. Een heel speciaal en blij moment in jouw levenspad. I'm gonna swap English-Dutch intertwined here, okay? As many of you in the audience know, at the end of this 4-year journey, I always try to reflect a bit back on my students. This ever becomes more difficult as the number of students increase to be original, okay? Well, Vincent made it easy for me, and there is a reason for that, actually, because I know him since quite some time, right? Which is not always the case. Huh? Yeah, I have many anecdotes, because the longer you know a person, the more anecdotes you assemble. So you're gonna have to listen to a few, all right? Actually, the first day I met you, I don't know if you recall that, but that was quite some years ago in the second bachelor with several of the people in the audience, in fact, who are also were together with Vincent students who had to, no choice, attend my course on science communication. That course is an outlier, and our chair knows it very well because he also lectured that course before I took over, in fact, from him. It struck me after the first class what a cohort of strong students I had in front of me that year. And the fact that several are here in the audience finishing their PhD confirms that I was right. Many of you did a twin bachelor in physics and a bachelor in mathematics, and you were one of them. And these students sometimes tend to be highly ambitious. And then there is this course where they have to learn to talk in front of an audience. And these students don't necessarily want to do that. And they mainly want to get high scores. And some are worried about that for this course, particularly after they had heard me explain the tasks I was demanding on how to give a good talk and how to become a journalist. These were the tasks. Well, today we have seen it's useful to be able to give a good talk, right? Some students expressed their worry in like, how can I get a high score? You also had a worry. Not about scores, not at all. Vincent came up to me after that class and he had a real worry because as it happened, these twin bachelors have a major and a minor subscription, and Vincent's major subscription was wrong because it was in mathematics and not in physics, should have been physics. And he was worried because that implied he had to attend this course with a mathematics lecturer. And he made it, and it's in bold, absolutely clear to me that he did not want to do that in mathematics. And he was also backed. So our first encounter, when he was a student with very short hair at that stage, still, I learned two things about you. And they are still true today. You know what you want, and you are not scared of saying it, even if it's a professor. You have to say it too. And also, you were backed by a soulmate standing straight next to you, saying like, yes, he has to be in this course with me. And that was Simon, who is in the audience, and who graduated last week. Yeah. And I saw friendship, and that is still active today, which is very important. So that was my first encounter. Vincent is the only PhD student so far that I supervised who, with several of you, obtained 4 undergraduate diplomas in 6 years' time. That's courageous. He did not only want to do this twin bachelor, but also a twin master, because even though I just said that you know what you want, you had a little bit of doubt what would be most interesting, theoretical physics or astrophysics. It became, I think, quite clear that your passion lies in computational astrophysics, as we heard today. And so that's also where you got your best master thesis. Too bad for the theoretical physicists. You even won a prize with it from the Belgian Physical Society, so that is absolutely worth mentioning. And I remember I had offered 2 master thesis topics at that time, structure inversion and rotation inversion, right? And then Vincent came up. There was another student interested, so I had to split them up. And his opinion was quite clear. I want to have the more difficult one. And as we saw today, you're doing both topics actually nowadays, okay? So this also characterizes you actually. And along with doing that, Vincent also wrote his own pulsation code. Very, very few students manage that, and this is impressive, but that's because, yeah, it's so much fun for him, right? Als Vincent over zijn code praat, dan vind ik dat zo als een klein kindje dat zich amuseert in de speeltuin. En ik heb nog een unieke situatie. Tot nu toe ben jij de enige doctoraatstudent, en ik heb er toch veel gehad, voor wie ik erin geslaagd ben om een afspraak te bekomen met koningin Mathilde. Wow! Wij mee op staatsbezoek naar Berlijn. Eén probleem, Vincent draagt altijd uitgelodderde t-shirts en sweaters. En zo ga je niet naar een koningin. Dus hij heeft toen een pak gekocht. En het staat hem goed, hè? Ja, dat ging helemaal goed. Ja, ik zal straks een beetje terugkomen op die t-shirts, want meestal heeft Vincent t-shirts en sweaters met nerdy codetaal aan. But what I mainly want to do today is also to thank you, Vincent, for these past few years, actually. You made it very easy for me as a supervisor, and I learned a lot from you. And so I hope also a little bit the other way around. But I want to tell the audience, when Vincent needed me, he asked an appointment. That's the way how I operate. But it wasn't so frequent. And when you came in, you always had very concrete questions, and the meetings were always very efficient and short. And so the last 2 years, I actually experienced you more a colleague than a student. And so thank you really for that. You're a colleague scientist. And especially also, you are a good promoter. You have shown that today. I was happy with that. I did write my letter yesterday. But you pointed out to your master student, Jelle, who is indeed somewhere in the audience. Ook een prijzenbeest ondertussen. He beat you already because he won 2 prizes and you only one. And me 0 as a student at that stage. So it's always nice to do better than your supervisor. What was very nice is that Jelle, by the way, hij wordt binnen 2 weken de Benjamin onder mijn doctorandi. Dat is leuk. Ik heb jullie onder elkaar laten doen voor die masterthesis. Want ik was absoluut niet nodig. Ik kon mij permitteren om als een voetbalcoach langs de zijlijn te wandelen en het spel te volgen. En dat is toch ook wel een kwaliteit die ik in de verf wil zetten. Thanks again also with Anna Chiara, who is also sitting there for organizing the Mesa School. The biggest one so far. Mesa School is an international trainings event, let's say, that came to Leuven. And when Vincent came back from his participation in Sydney last year, he walked up to me and said, I'm going to organize the next one. And I thought, oh my goodness, Vincent, this clashes with the submission of your thesis. But he has shown that it worked very well. Some witnesses in the audience can justify that. And it showed me how strong you are in disseminating and training young people, young and old. I see Claude in the room. That's nice. Thanks for being here. And you have done so many years of that with Ulysses, which is a student association, which is quite important for Vincent. And so I want to mention it here. In mei van dit jaar vonden we allebei dat de speeltijd nu toch even moest stoppen. Het zijn jouw woorden. Hè? Want die publieke verdediging kwam eraan. En dan moet je toch even weg uit de speeltuin. Dat moest van mij. Dus ik heb niet dikwijls gezegd dat iets moest, maar dan wel. En ik heb gezegd, tot je publieke verdediging moet je uit de speeltuin. Voilà. We zijn er. Hè? Dus je mag nu weer terug in de speeltuin van het coderen. Hè? Je hebt ook nog vele plannen, hebben we gehoord. Je hebt ook nog je eigen financiering om te doen een jaar wat je graag doet. Ik heb voor jou eigenlijk een cadeautje bij. Moet je straks maar eens bekijken. Dat cadeautje gaat het aangenamer maken in de speeltuin, want dat kostuum is daar nu toch niet echt voor geschikt. Hè? Dus dat kan je straks even bekijken. Vooraleer dat ik wil afronden, wil ik toch ook graag een woord van dank richten aan de ouders van Vincent. Familie en vrienden in een volle zaal. Ik stel vast dat de zaal eigenlijk te klein was. Ook dat is een statement. Het was een privilege om Vincent te begeleiden. Het is dankzij zeker jouw opvoeding en jouw ouders en steun van vrienden dat je toch ook staat waar je staat. En ik hoop dat wij daar allemaal zo dadelijk samen een heerlijk glas op zullen drinken. Van harte proficiat, Vincent. Je mag het openmaken. Het is een sweater.
All right. So, next along is. Well, first of all, thank you, Connie, for those wonderful words. I have to. You have to. I did not completely leave the playground. I could not resist that. So, but yes, it did help that you pushed me a bit in the right direction at that time. But yeah, otherwise, I think it has been amazing to work with you these past 4 years, both in terms of the advice and support you gave me, but also by allowing me to do my own thing as well. So, thank you for that. And I'll have something for you here. I'll have to come around. Build up some suspense. Well, there's 2 things here. I'll start with this. Most of you know that Connie likes bubbles. So there you go, Connie. And I have also something, I would say maybe a bit more special. That's in here. So, so what you have in your hand there, Connie, it's a bit of a prototype.
Oh, do I need to open it?
Yes, you can, you can.
Okay. Feels like something delicate.
This version is not that delicate.
Oh.
So this is the mode cavities, or the mode propagation of a specific mode in a specific star. And it's not the star that I showed here.
Oh.
It's let's say, close enough model for the HG 129929.
Ah, my star.
Your star. So that star has nickname Connie star. So this is currently a prototype in plastic, but I intend to make it a bit more fancy. But that I wasn't able to get that done before the event. Yes.
In my heart.
Yes. All right. So I'd like to thank all of you again for coming here, everyone online for following, and of course for all my friends, colleagues, family, parents. Thank you for supporting me during this 4-year journey and before that even for a whole bunch of you. I think since it's almost 6, so I think I suppose most of you have a dry mouth and maybe start feeling some hunger. So please go outside and have a drink and grab something to eat. Thank you. Unfortunately, for those following online, I can't offer you a reception.
doctoraat in Nederland. En dan komen ze na een tijdje zeggen